Hey everybody, Sluggernaut here. I just wanted to create a video today that kind of at least attempts to exemplify the difference between fragmented and contiguous memory in C++ and try to discuss cache misses and hits and kind of what's going on in C++ and with containers and different things and pointers. We're going to kind of cover a little bit of everything. This should be a fairly quick video though. Real quick, all we have right here is just a class called timer that starts the time when upon creation with the constructor, and then when we call stop or of course destruct, fall out of scope or whatever, stops the timer, and in if defined to do so, prints out that time. Keep in mind that this end time happens immediately, and then we have our calculation and print it. So none of the rest of this calculation should have anything to do with the actual time being displayed. And so let's kind of get into our example here. So we have a class here called linked list. This is really like a linked list node, technically, but we're just going to call it linked list. It's as dead simple as I could possibly make it. We have a default constructor, an overloaded constructor that sets our payload. We only have two integers, just a nice, simple bit of data. And then, of course, in linked list node fashion, we have a pointer to our next, which is by default a null pointer. And then I have a quick set function, which is just a helper function for me. Yes, I understand that this is a struct, and this is all public, and I could set these without without this, but anyway, just makes the code nice and clean. We have a quick helper function here. I'm actually not sure if we ever use this. It doesn't look like we do, so ignore that for now. Here's kind of the crux of the matter. Of the three different linked lists we are going to go through, they are made in three different ways, and but they are iterated through in the same way. We start with an iterator that starts at the head of the linked list and then iterates by going to the next node in the list, or next linked list object in the list. So they are iterated through not with pointer math or anything like that. We are actually trying to fetch the next object in the container with the pointer. And this is, again, kind of the major crux of the matter. Typically with an array or a linked list, that is the major difference between the two. When you're iterating through an object, you're basically using pointer math, depending on kind of what you're doing. But you're usually going to use pointer math if you have contiguous memory, and you're going to use this style of loading the next object by fetching it in a linked list, or I don't know, maybe some other type of iteration container. So let's get to it. In our int main, the first interesting thing is by the way, we're going to be creating 3,000. Our number of items is pound defined as 3,000, and we can see why in a moment that I had to pound define that. It's basically for putting memory onto the stack. And but here we create our standard linked list, just starting from an original pointer, and calling new on each individual item, and then iterating through and creating next, and making sure each node points to the next node, and we don't lose any memory. We reset our iterator to the head when we're done. The next linked list is made by calling new and setting this number of items. So we have one big array of contiguous memory on the heap in this case that is allocated and then created, where we have to set our next pointer to each next one so we can iterate in the same way, and then again resetting our iterator and head pointer, and then technically in our program here we kind of test those immediately, but I then decided to create a stack version. This is why I had to do a pound define on number of items, so that this number here I wouldn't have to call new. And you can see that so right here our memory is allocated on the stack, and it's just 3,000 linked list objects in contiguous memory on the stack. And so lock in your answers now. How do you think those three will perform in succession? I want to point out also that I am in release mode for this test. When you run in debug mode, the compiler and debug symbols and memory padding on all this can kind of add a lot of overhead, and I want a real world one-for-one test that we can do. So if we go ahead and hit F5, we will see immediately that our normal god-awful linked list took 8 microseconds to iterate through, whereas our heap memory took 3 and our stack memory took 3. Now, if you've heard that the heap is slower than the stack, that is honestly not true. They behave in the same way. They are both just allocations in RAM. The memory has to be fetched and put eventually into your cache and into a register to be read by your CPU. They are exactly the same. Allocating memory on the heap is slower than the stack. The stack is pre-allocated memory. When the program is created, the operating system allocates memory for us to use locally. And this is extremely fast to then just write over some of that memory that has, again, already been allocated, and then use, so, our unsigned integer in our for loop, right? This is, we don't call new here. This is just stack memory. Whereas anytime we call new, that is heap memory. Again, this, we have to, when this is called, we have to ask the operating system, hey, can you please find me a contiguous piece of memory and allocate it that is of this size. Whereas for the original linked list, of course, we have to ask this over and over and over for a much smaller size. But this is, if we were to, I think, time this for loop and this for, or and this, let's be fair, this allocation and then for loop, this would be much faster. It is one big call, and as long as our RAM isn't already filled up in some way or something like that, we should be fine. But that's a completely odd edge case where you're reaching the limits of your system and have undefined behavior probably within the system itself. And so let's just run that program a few times and see if we can get some interesting output here. Here's some interesting output. We had a bit of a slowdown where the god-awful linked list, as usual, takes longer than the contiguous memory on the heap and the contiguous memory on the stack. That is expected. This should always be slower because of the memory fragmentation. And if you still don't understand memory fragmentation, basically every time you ask your operating system, or let's not call it the operating system, every time the program tries to allocate a piece of memory and read it, there's usually an extra sort of buffer where additional memory after that memory, and I've heard sometimes before, but I'd love to try and prove that with another program because I'm not sure about that, is loaded into the cache. And then once it's on the cache, it can it will be a cache hit when it needs to be put into the register and read and output and whatever it's doing. So basically when I'm asking for, let's say, the third or fourth item in this linked list of 3,000 objects, it's going to load the third, fourth, and fifth, let's say, depending on the size of the data you have and a bunch of other things. And so we will then try to ask for the fourth, and it's already on the cache, and we can load it into a register. And we ask for the fifth, and it's already loaded on the cache. Then we'll get a cache miss, and it has to be fetched from RAM, put into the cache, put into a register, etc. So we can see how this would be much faster. Now, the other interesting thing here is that the stack was slower. And this is because it's just the general volatility of RAM and memory and fetching and cache sizes and misses and all this stuff. We kind of expect this to happen at least a little bit, but these two numbers should almost always line up. And this number here for the god-awful linked list should always be any amount slower, twice as slow, 3 times. It is also going to bend, by the way, on the size of the object. If I had these linked list nodes just chock full of tons of data, variable sizes of data, they have arrays of varying sizes depending on this object and what we're working with. We're going to have all sorts of weird numbers, but again, we will always have a slower linked list than contiguous memory. Or at the absolute worst case, the same amount of speed, and only in some very odd case where something else was happening on the system would we see a heap, any contiguous memory be slower than our fragmented memory. You'd have to be doing something very, very strange, and then in the middle of your process, it's very strange having extremely large objects that can't have um, multiple units loaded into the cache at the same time, and then uh, also those objects like during this iteration of these different um, containers have something very strange happen on your system where it suddenly, the processor was overloaded with other things. Your antivirus, a game was loading, any sort of odd thing, or if this was in a multi-threaded process and something else from the main thread was spawning other threads at the same time all of a sudden, so the scheduling was messed up. Very odd scenarios that you will almost never really see, though you should be aware of them in case you do have a very odd process and you're doing very, very deep dives into the performance of your system. So, anyway, hopefully this helps somebody. Hope you learned something. And I'll go ahead and post the code. Let me know where I should post this code, if anywhere. And yeah, I just want to repoint out again. I've never seen this before. It's very helpful for my IDE technically to understand that I'm allocating onto the stack a very large amount of data. Um, that was pretty interesting to me. So, um, wonder if there's a way to fix that. I wonder if it thinks that I could just put this in its own scope. And so as soon as we run out of this particular scope, um, no, okay. I was just curious if it would kind of trick it into thinking, hey, it is on the heap, but it's scoped in and not the lifetime of the entire program. And definitely if we put this at the top of our program where it's allocated before all of our other um, things, this could cause other issues. Again, probably not in a program as tight and small as this one, but if we had, a massive game call in here after this allocation, and we didn't have this local scope, and so on. So I'm kind of rambling now and just pontificating on more odd scenarios and things where we want to make sure that we wouldn't be allocating this for the lifetime of an entire program. So anyway, let me know if you have any additional questions, if this helped anybody. I did make a Reddit post on this yesterday, and some people already gave me some kudos and were interested in the general idea of the type of iteration doesn't matter, but the stack and the heap and the fragmented memory make a large difference and that kind of stuff. So anyway, thanks everybody. You have a good one.